So, welcome to my talk about little Kotlin multi-platform treasures. My name is Marc Reichelt, and you can find me on Twitter at mreichelt, and I work as a senior Android developer at Snap Mobile. So, let's get started. So, let's go on a journey, and by journey I mean an adventure, and find some treasures on the way. So, what do I mean when I say treasures? So when we work with colleagues, then we will have these conversations like, oh, we are working on some with the IDE, and then our colleague shows us some new shortcut, and that makes us more productive. And I call these things treasures. It's just, things that make us more productive, or ideas we didn't have before. And I collected some of these treasures on my own, which are around Kotlin native and multi-platform, and I guarantee you that some of you have not seen yet. So let's define what is a treasure so we can actually hunt them. And I found out by astoundingly that there's no emoji for a treasure chest. So please, 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 if there's any Unicode people, any people with contact to some emoji person, some people behind Unicode, hey, the treasure chest is an emoji that we really need, or at least I need it for my talk anyway. So we will see about treasures, and we're going to dive deep into Kotlin native and into Kotlin multi-platform, and let's see what we find. We'll start with Kotlin native. Small disclaimer, this is going to be a live coding talk, so I mean adventure for real, because it's going to be an adventure for me, and it's going to be really fun for you to watch me if something fails, but hopefully the demo gods will be kind to us, and we'll have smooth sailing all the way. Let's see. Sorry, hey over there, could you please move away if you talk? Thank you. Okay, let's enter the presentation mode here in the IDE. And I shared this project on GitHub, so I will share the link later on. And we have different Kotlin multi-platform modules here. And we're going to start with the first one, which is called 01 native. And here we have a really simple common main hello world function, which I'm not going to show yet. And we set it up in the build Gradle file. And we basically say, hey, we want to build some Mac executable, some Mac ARM executable, some Linux binary, some Windows binary, some JavaScript, and we're going to build an iOS framework. And I actually built that before. And we can see how this looks like. So here we have the bin folder. We can see all the executables there being created. And for example, here we have the Linux folder, and there is the program right there. And here we have the Mac folder, and we have the program right here. And we can just execute it. So let me go to the terminal and actually execute that binary. Okay, and oh wait, I wanted to execute the Mac one, because the Linux one, of course, is not going to work because I'm on a Mac. And here we go. Hello, droidcon London. But that's not impressive. What I found out actually is there's a small tool which you can actually call where you can just know what's inside of the file. Now, let's say that we don't have the source code of this file, so we can actually inspect and look inside of these files. And one tool is actually called file, and we can just point it at any binary. So we can just type file, and we type the file name, and then it's going to show us some information about what's actually inside of this file. And it doesn't look at the file name, it really inspects the first bytes, and then says, okay, this is a Mac 16-bit binary for ARM64. And that's really nice. You can actually call that on different files, on PNG files. It will actually always tell you what's contained in that file. And that's really, really powerful. So let's say we have not just this one, but we want to find all the exe files here. Just wait a minute. OK, here we have the executables. Let's actually limit that. So, And now we can actually call that for all the other ones. So let's just see the files. Here we have the files in our bin folder. We can see the different sizes. Of course, the debug executables have larger sizes. And now we can actually call the same command for all of these. And we can see that inside of the Linux binary, there is a Linux executable. We can actually see that there is debug info inside or not for the Linux binary. We can see that the MS-exe files are actually containing Windows bytecode. And that's already getting us started. And the tool file, I just drop it and I just call it on any file I want to get some more information about this. So what if we would like to know a little bit more about the file? Like, for example, so usually if we have some program, it's going to be linked against some shared libraries, and we want to know that. For the Mac binary, you can actually call a tool called otool, and with the uppercase L parameter, you can give it a file, like a macOS binary, and then we can see which libraries this is actually linked at. And we can try that for Linux as well. And we're going to see that this tool needs, wait a second. So here's 01, okay. And we can see that this is actually not an object file because we need a macOS binary for this tool to work. But there's another tool called object dump, which we can call with the parameter p, and then we can point it at any executable, and it's going to show some info. And if we just want to know which libraries this is linked against, we can just filter about the needed, and now we have the libraries, the shared objects. On Windows, you call them DLL files. That this binary is linked against. And that's already pretty helpful. What's also nice is another tool. So we have learned about file, we have learned about otool, we have learned about object dump, but also what's really cool is that you can find the strings, the ASCII strings inside of the binary file, and the command is actually called strings for that. And that's really helpful. And you can see in the native binary that we have lots of different functions which are actually human readable. But we can actually filter like before, and we can just filter for Kotlin, for example. And then we can see that all the Kotlin things like hash map and everything is defined. And that's, of course, because the Kotlin standard library is linked with the native one. It's not just linked, it's built into the binary. And that's why we find these definitions here, which are still human readable. So the question is, can we use this tool to find the treasure which is hidden inside of this executable? I happen to know there is one. So let's actually search for the treasure. And it's going to be some uppercase or some case insensitive, but we don't find it because in this case it's an UTF-8 string, which is a little bit more complicated to find because it's a different format than ASCII. So now let's go over into the danger zone. So we can inspect the binary, and actually, for Java, we have really nice tools. We can just, disassemble the class bytecode, and we can decompile it to some Java code, which is actually really nice to read. But what if we have a binary? Well, turns out, a friend of mine actually told me there's a tool for that by the NSA, which is actually open source since 2019. And of course, you only should use it to inspect files which you are legally able to. So in this case, we are building the program ourselves, so it should be fine. And we're going to open the tool, which is called Ghidra. So let's open Ghidra. Yes, I agree. Did this before. And actually, when the friend of mine showed me this tool, we were in a bar and actually having this open, and we were talking about it. And then the waitress came to us and asking us, like, "Are you hacking somebody?" And we asked, why you ask? And this is what she saw on our screen actually at that time. Well, we hacked ourselves. That's it. So we will now create a new project. This is just non-shared project. Just enter some name. Doesn't care. And now we can drag and drop the file from the IDE. So let's actually open the folder here, and we will inspect the Linux binary. Okay. And I'm going to drag and drop the file here and then it's going to show some information. I'm going to skip a little bit over this because we don't have so much time. It's going to show some valuable information about this, like, for example, which format it's in, which address, which libraries it's linked against. So here we have the information as before. And now we're going to analyze it. And we will actually decompile. We can actually see the assembly bytecode, and we can now analyze it, run some analyzers here, and we can actually now disassemble this into C code on the right-hand side. So in the middle, we're going to be seeing assembly code, and on the right-hand side, we're going to be seeing like what C code could have been written to actually get this program running. But of course, we didn't use C to create it. So here we are. I'm going to zoom into the things that we need. So for example, here on the left-hand side, we can actually filter for things. So we can enter Kotlin. We can actually see that all these types are here defined. We can see some labels defined, maybe some functions defined. And let's actually jump to the Kotlin main function. This is the main entry point. And now I'm going to double-click. Here we can see the C code. So here we see that it's calling some init and run start function. I'm going to double-click on that. And now we can see the C code of this main function, which is actually pretty cool. But can we actually get what it's doing? And the nice thing about this is we can see here that this thing is actually doing 2 print lines. And we don't have the variable names because that has been compiled away completely. But we can actually double-click on this unnamed thing here. And let's see. So this looks like that it should be taking a string because it's a print line. But the data doesn't really look like we want it to be. So we happen to know that this data is actually should be a string or a Unicode string. And then we can see here. Can you see it? So we see the string, and it's just, there in the assembly code. But what's cool about this, we can actually right-click here at this position, because the string, of course, has some bytes before the actual Unicode string. We can just say Unicode here, and there we go. But we didn't find the treasure yet. So here we have another print line, which we didn't see before. So when we ran this on Mac, we only had a single print line. So what's here? So we can actually go here. We do the same thing. I'm just going to press Y, which is going to do the same thing. Here we see some text, some treasure found. We can actually see that. And here are some other things. So let's actually mark that as a Unicode string again. Now we can just copy the value. And now we're going to go over to Android Studio. And let's see what we just copied. So we're going to just copy it here. And there we go. We have our first treasure. So now we have learned something. Now we can inspect a binary with GDRA and actually find what's inside. And what's really nice about this, IntelliJ should do this. Like, you can also do refactorings in this code. You can actually rename the label. So I pressed L to rename the label, and we now know that this is going to be a hello world string, and we know that this is going to be our treasure string. And then we can just rename them, and this way we can, inspect the binary, because we now have to reverse engineer it and actually see and rename the variables to the meaning that we give them to. And of course, we're going to fail because sometimes it might have one meaning, but sometimes it might have a different one. So that's the GDRA tool. Let's actually quit that. So then we go to the next one. So we're going to actually skip the next one. So the first program was a little bit easy. So it was just a hello world function. So this one is actually computing the distance between 2 locations. So in this case, I'm actually computing the distance between droidcon and my hometown, which is Frankfurt, which is going to be a little bit between 600 and 700 kilometers. And I'm going to leave it up to you to find the treasure inside of this binary which is being built. But it's pretty cool because you can actually see that it's calling into the C math functions of cosinus and sinus. So that's pretty cool. Now, the next thing I want to show you is, so we have a Kotlin native binary. What if we would chip it? Like Hardy said, okay, we can just chip the machine so we can create a Docker image. And that's actually really simple to do with Docker. A friend of mine just told me did you know that you can actually create a Docker image, in theory, that only contains a single file, which is the binary? And that works if the binary is self-contained, so all the information needs to be there. All the shared libraries need to be included in the binary. And that's actually what Go does by default. So every Go program is actually usually self-containable. So this is not the case here, but we can see in the Docker file that this is going to be, we are starting from an Ubuntu system, then we will copy over the program that we created before with the location, so I'm actually showing that. And then we set it as entry point, so that means that if we run the Docker container, it will just go ahead and start the Linux program that we just included. So this is inside of this build sh script, so nothing going on there, just copying, just building the Docker image. Now we go to the terminal, and we enter the folder. We call build. So we build the Docker container. And there we go. That was it. Now we can see the Docker images, and we can actually see that there's a droidcon image, and it is like 80 megabytes. OK, that's cool. Oh, and of course we can run it. We can just call docker run, and then we call the droidcon image. So I'm going to call that again. So here we have. And there we go. And now we found another treasure, which is we can now build Docker images with a single binary from Kotlin native, but you know, all of the other stuff is still there, so the whole Ubuntu image is still there. And that's the reason why it has 80 megabytes. And it's actually good that it's there because it's needed, because we need the shared libraries. So, but what if we could shrink it to the most minimal size that we want? And the nice thing actually is that we can do it like this. So basically, we're coming from Ubuntu as before, and we can actually use something. So I learned this on the way when creating this talk. You can actually use some image as a build stage, and then you can just create your own image from scratch, which means nothing. And then we just use this as export stage, and then we just copy over the shared objects that our binary needs. So these are the first ones that we saw. And because I'm actually using something more, it's actually using more shared libraries. So we copy those two. It's used for OKIO and actually accessing files inside of this Docker image. And the other things are the same as we saw before. So now if we go here and we build the image, same as before, and now we can see that the Docker image is much, much, much smaller. So it's actually 4.6 megabytes. And if I wouldn't do the native calls, it would be actually like something like 4.1 megabytes. Isn't that cool? So, and now we can also run it. And there we see another treasure found, which is now we can build tiny Docker images. Wouldn't recommend it though, because as soon as you call, if you include another library, and that needs a shared library, which we didn't have there, you need to make sure. So you need to run your program to actually find out which shared libraries you actually need. But it's a nice hacking session, and actually getting to know this, it really showed me how Docker works also under the hood. So it's quite cool. So with that, we're going to go to our next thing. So I'm going to skip over this a little bit faster because this is included in many talks. So of course the demo, if you create a new shared project, a shared Kotlin Multiplatform project from the IDE, it will actually only create you one Gradle module, which is the shared module. But basically in the real world, we have lots of features. So practically, we want to have multiple modules actually and then those interconnecting and actually, using one module from the other. And then for Maven, we will for Java, we will have multiple jars, and for iOS, we want to have one single XC framework. So, but this is basically so here we have one module, and we have 3 feature modules inside. So here we open the build Gradle KTS. And basically, we're just defining that we want to have JM, JS, and the iOS targets. We want to give it the shared base name. And then we can actually call implementation on the individual feature projects. And that's basically how we include. So it's basically working like we expect from all other Gradle modules, which is a good thing. So it's actually doing something what we expected to. And now if we go here in the SRC folder, so we have the 05 multi-module project, which includes the other features. Oh, by the way, I didn't show how these actually look like. So here we have just JVM.js and the iOS and iOS simulator ARM64 definitions, and we built some code, and we include that in the 05 multi-module project. So let's cross our fingers that this works. So here we have some print all features function, and we actually have a test also in the common folder, and we include all the other feature folders, so we can actually run the test here. Let's see if that works. And we can actually select all the targets, so we can actually run this on an iOS simulator, in a browser with JavaScript, and on a JVM. And I'm going to select all of them. Let's see if it works. And it's actually, so JVM and iOS test is already done, and the JS test too. We can see that all tests worked. And then we have another treasure, which is the knowledge about how to actually compose multi-module projects in Kotlin Multiplatform. Nice. So, and you know, by the way, this was running pretty quickly, actually. Of course, I built this before, but it's really nice to see that we can actually call these tests on 3 different platforms at the same time. I think this is really powerful, powerful feature to have. So, some amazing kudos to the JetBrains team for doing Kotlin Multiplatform in a way that we can actually, you know, do these things, and in a simple way. Okay, now creating a multi-module project is actually, it's okay, it's easy to do, but publishing it to local Maven Artifactory, for example, or to a remote position is actually a little bit trickier, but I'm going to show you either way. And this is, you know, now really danger zone live coding, like many things can break, so let's see if this part of the presentation works. So here, we're going to have 3 features. I just replicated them, so I didn't mess up with the other Gradle modules which are inside. And basically the only change that we did to before was that now we include the Maven Publish plugin in these features. And we not just include them here, but we also include them in the build Gradle file. So here, and actually we defined the Maven Publish configuration at the top level, so we here at the top level build Gradle file, basically what we need to do is actually setting the group and version for all the modules which we want to export, which are these projects right here. And this is going to make sure that the Artifactory has the right Artifactory ID, so it doesn't rename it in a funny way, which we then have to deal with later on if we publish it to somewhere. And this is going to can come in handy later. So we're actually going to do it live. I'm going to go and start an Artifactory inside of a Docker image locally and try to publish to that. Let's see if that works. But let's get started with the Maven Publish first. So we have the projects. We can actually go into the folder. And now to publish, we can actually just call the publish to Maven local task. And now it's published. And what did that just do? We can actually look in the M2 directory on our local machine. So it put the features there, and we can see that all the artifacts that we just compiled were created and were published to our local Maven repo. So if we would include them in a different Android applications, we can just, you know, add Maven local as a repository, like we would the regular Maven repo, and then we can just compile with the local sources. So that was pretty easy. So now I'm going to start an Artifactory image, and this will actually take 30 to 40 seconds to run. So we're actually going to run that in the background. So how we set up the Artifactory here in the build Gradle KTS was we set up, wait a second, this was the other one. So here we set up a name which is called droidcon repo, And we set up the local URL, which is the one I export from the local Artifactory, which I'm running, which I have set up before. Here we get some droidcon username and password, which we need. That's good that I remember that. So I actually have to export them on the shell. It's not really, secret to us right now. It's just running locally. And now we should be able to actually publish this to the local Artifactory running, to the local Maven. So not the Maven local one, but an Artifactory that we are running, which could be running on some server somewhere. But in this case, it's happened to run on my machine. So let's go ahead, and we can actually call gradle tasks to find which tasks we have, and we're going to filter for the functions about publishing, so we can see what's there. And here we have the publish functions, and I think what we need is going to have this one, publish all publications to droidcon repo repository, which is the name that we gave it. So if we would have named it foo, then there would be foo inside of this task name. And now we can just call gradle and actually publishing. And now it's uploading those. Oh, it works. I love it. It's now uploading these files that we saw in the Maven local folder. It's uploading those to our Artifactory. And sure enough, if I now go here back to the browser, and we go to localhost, we can see that the Artifactory is running. We can log in. And let's see if we can see the artifacts. I'm going to make this a little bit bigger so you can see it better. So here we have the droidcon Maven repo, which is where we just published the artifacts. And sure enough, here we have com, example, droidcon, and 06 publish, and it's all there. So we just published all of these. That's pretty cool. And it works. So that was the easy part, actually. That's now, publishing to Maven local. That's publishing to an Artifactory. So what if we want to create the Swift package for the iOS framework? So you could create the XC framework, but actually the Swift package format in iOS is pretty simple, actually. Deploying it, on the other hand, is not. We're going to get to that in a minute. But actually, if we just go here, and we want to build a Swift package, so I'm going to show you how that is set up. So I'm going to close these files, open this one. So this is how we build the XC framework. So that's pretty simple. We just call the task. We say the base name is 06 published, so that's going to be the name of our Swift package. Then we add the targets, the different iOS platforms to this XC framework, and then we just export the projects to the XC framework. And if we look here, if we just look for the create XC framework task, there's a task which is called assemble XC framework. You might have heard about that already. So we're going to call that and actually assemble the XC framework. And that's already been done, so that's nice. But creating the Swift package is actually having two things. So we just created the XC framework, which we can see here. So here it's in build. We have the XC frameworks. So here we have, for example, the release one. And it's basically containing all the architecture. It's going to contain the ARM64 architecture for the real iPhones, for the real iOS devices. And it's going to have another framework, which is actually having two architectures inside, because that contains the ARM64 simulator native program and the x86 one. So that means that if I would ship this to my colleague and that he was not lucky to get an M1 machine yet, he will be able to run the framework as well on his machine with the simulator. So we have this framework, and now in order to do a Swift package, what we need is actually one single file, which is called package.swift and just has some Swift code inside, and we're going to need the XC framework, which we just zip. And the only complicated part about that, actually, in building it, is that if we want to distribute it somewhere and we want to say to the package.swift, hey, we want to download this from some URL, it actually forces us to include a checksum, which makes sense. So we actually check that the file has not been corrupted in any way. So that means that if we want to build this, we what we need is actually this package.swift file, which looks something like this. So here we have the name. So this is going to be created by our Gradle tasks. So I did this all myself. There are also plugins you could use to actually create the Swift package. But I prefer to do it my way, to do it on our own with some Gradle tasks, because we couldn't use it actually when some Kotlin upgrade came with a version. We couldn't actually use the plugin, and the plugin defines a big DSL for creating the package.swift, and we actually don't need that. We can just create the package.swift, just a string actually. We can just create that ourselves. Just write v14 here. We just have to exchange these, and we just have to pass in the URL where we want to have the artifact to lie. That's the zip file, so that's actually going to be the zip file that we want to deploy. Oh. And here we have the checksum. So what we can do here is I'm going to go back to our Gradle file. So I'm going to define all of these targets here, which is so tasks. So we're going to create the zip. So we're going to zip the XC framework, which is defined here. Then we're going to compute the checksum and put into a file. And then we have the checksum, so then we can just create the package.swift file, which is just writing a file to disk with the checksum that we calculated earlier. So this is all we need to actually create the package.swift. So if I call this task now, it's running, and then it created what we can see here. So it will create the zip file, it will create this checksum. Let's actually delete this file so you can actually see that it's working. We can delete the zip file, we can run it again, and we see that they have created basically instantly and quite quickly because the framework was already built. So that's nice. So now we created the Swift package. Now how in the world do you publish it? And I noticed that just a couple of weeks ago there was the droidcon New York, and Nate Ebel had a nice talk about combining brownfield applications with Kotlin Multiplatform, and it turns out that they were doing like the similar thing that we did. So we found out that we are on the right track, and we actually solved the problem also because if you just would push the zip file to a Git repo. So in Swift packages, you just basically push all of that into a Git repo, but it will grow pretty quickly in size. And they had trouble with sizes of Git repos being like 5 or 6 gigabytes in size, because Xcode will download the full Git repository with the full history actually, which is not that ideal. So what we're going to do is we're going to publish the package.swift to a local Git repo which we have, and we're going to publish the zip file to the Artifactory. And that's why we can see the Artifactory URL here, and we could see it in the package.swift. And the way that this works is, so I'm going to now go into the details. So here we create the Swift package manifest, which depends on some other tasks. Then it depends on the checksum file. And it depends on the version. So if the version changes, then we want to basically recreate the package.swift file. So we make sure that we upload a new thing. And then we just use some Kotlin code here in the build creator. So that's really awesome that we can just call Kotlin here. We can just create the string, which is the package.swift. We pass in the URL and checksum, and then we just write it to a file. And sure enough, and later on, so this is creating the package.swift, and now with that package.swift we can deploy it to Git, which is actually done by a script. So I'm just calling a script here, which I called deploy Swift package manifest to Git. So that will actually make sure that we pass in the version, that we push the package.swift file, and that we also create a tag locally, and that we push it to the remote Git repo. And then in the deploy Swift package, we're actually going to call wait a second. So this is the package manifest. This is the Git repository part. And then there's the Artifactory upload part. And here we just rely on the zip.xc framework. So we want to get the zip file. And we want to actually upload it to the Artifactory. And this is basically all you need. You can just call a curl command with username and password. You can give it the binary data. You can put it. And then if we do that, now this task here, which is called deploy Swift package, it will actually combine all of these tasks. So because we have to make sure that we not just upload it to the Artifactory, and that must work, but only then we can create the tag. So both have to succeed. So let's see if that works. Okay, deploying Swift package. And now it failed. And the reason for it failed, let's see why. So here it says no changes for version 1.0.0 snapshot. So it seems that I already deployed this version one time. So I'm actually in the script. So here we have the script. I'm actually relying on a local Git repo, which I just have sitting in my home directory, and we can just recreate that. So we're going to go to my home directory. Let's remove the repo which is there. Okay, and now we can just create it again. Okay, and let's see if that was already fixing the issue. And it didn't work. And this time it didn't work because maybe I closed the shell and then the Docker username and password is missing. So let's actually see if we can echo those. Ah, yeah, okay. They are missing, so I'm going to export them again. And now it should be able to work. Fingers crossed. No? Okay. And now the problem was still that it returned an error. And that's funny, actually. I noticed that if we go to the Artifactory, which we have before, I have to log out and log in again. And then suddenly it started working. I don't ask why. Don't ask me. Let's see. So we log out. We log in again. And let's see if it works now. It's still not working. Oh, okay. This is a different error. So it seems I published this particular version before, so it doesn't give me here. But if we look in the log here, we can see that we don't have the permission to publish an artifact that we already have published. So it's lying there in my Artifactory. I published it already, so I cannot upload it again. So we're just gonna change the version. It's actually nice that you can see all of these, which means that I ran into all of these problems when creating the talk. So now we can go here. We will define a new version. And now, hopefully, it works. Let's see. And it's uploading. Yes. So it's uploading. Thank you so much. Yeah. So it just uploaded the snapshot, it just uploaded the zip file to the Artifactory, and now it created the Git tag locally, which you can see here. And now if we go to the Artifactory, we can see in the artifacts, in the droidcon generic section, that we now have 06 shared. And sure enough, there's the 1.0.0 snapshot, which I already deployed. Maybe in preparing for the talk, I didn't delete it again. So we couldn't upload it again, but we uploaded the second version of that. So that works. I'm so happy that it worked, because this was the most complex thing in my talk. And now the last sample I actually want to show you is so how you can speed up your multi-platform builds. So here we have the multi-module project that we saw earlier. So it's kind of a bonus, which I reserved for if everything works. So it's nice that you get to see this. Okay, so usually now I'm going to do a cradle clean. And so I'm going to clean all the artifacts that I built before. Yikes. And now if I am going to build again, now it's building everything from scratch, which is going to take some time. And actually, some things could be improved in the Kotlin Gradle tasks. Like, for example, the linking doesn't seem so if you have 3 iOS frameworks, it will actually not link them in parallel, so it will actually wait for everyone to finish. So there's some chance for parallelizing things here, which I hope that the Kotlin team will work on at some time. And so this takes some time. So what if we don't have time for that? We don't have time. We want fast iteration cycles. And the way what we can actually do, and I included this in the script, basically most of the folders have some scripts, so you can actually do these on your own. At home. So here we say, okay, we want the clean, 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 we want the cle and we only want the check, and then it basically has to compile everything, again, and that's going to take some time. But if we only want to run the JVM test, we're going to do much quicker. So for example, here we just do the JVM test. That's much faster. And if you call it again, it's even faster, even if we clean it before. And you can do that for JavaScript as well, or only the iOS thing. So for example, in this case, we don't compile the other targets, which is ARM64 for the device and not the x64 architecture for the simulator, because we don't need them. We only want the iOS architecture. That's already faster. But mostly, if you work on Kotlin Multiplatform code, the nice thing is you can just call, you can just run the stuff you need, and that's going to go, and you will have a much faster iteration cycle, because if your test just recompiles in 1 or 2 seconds and you can just execute it, it's much better than if you would have to wait for 1 or 2 minutes, which it can actually happen if you have a pretty complex setup and lots of code. And if that has to be compiled natively again, then waiting for 2 minutes to just get a test running, and then the test fails and then you want to try again. So this is much quicker to have an iteration cycle of seconds or milliseconds instead of minutes. And that was basically everything. So that was all the treasures I wanted to show you today. So I hope you found some valuable ideas, valuable lessons, some treasures that you can take with you home. And we're not going to have time for questions, unfortunately, but please, if you have a question, just find me afterwards or just find me on Twitter, and I'm going to make sure to upload, to also tweet about the code, that you actually can check out the GitHub repo and, actually, disassemble a program yourself. Thank you.